So now that we have talked about composition of functions, and we've also talked about one-to-one functions, we can look at the topic of inverse functions. So the question is, suppose that we have a function that takes an x value to a y value. The question that becomes necessary for us to ask is there a function that takes us back? Now, one of the key things that we need to look at here is this statement right here. Is there a function that takes us back? If there is a function that takes us back, we call that function the inverse function. So you'll notice the inverse function simply undoes what the original function did. So if we start off with x, then the inverse function would act on y and take us back. So suppose that f is a one-to-one function, then the domain of that function is going to be x and the range is y. Then suppose that we have this function g that has the domain of y and the range of x. So notice those are backwards from what we saw for f. Then if f is applied to x, then g will undo that action and take us back to x. And then likewise, if g acts on x, then f will undo what g did and take us back to x. If that happens, then we have an inverse function of f. We call g f inverse, and we denote f inverse with a superscript of -1. Now let's be careful that -1 is not an exponent. So, since f inverse is not an exponent, that -1 is not an exponent, that does not mean 1 over f. You cannot just simply flip the function and that's the inverse. So notice that if y equals f of x, then x equals f inverse of y. And that's from this picture right here. F inverse acts on y and outputs the x value. And from this statement up here, f has to be a one-to-one function for it to have an inverse. So let's imagine that we have this function f of x equals 7x minus 3. Now we know this is a line. Does this function have an inverse? If we are to graph the function, notice that this function passes the horizontal line test, so therefore it's one-to-one, so therefore it has an inverse. So yes, it passes the horizontal line test. Now, notice this is a warm-up. We will never find an inverse by doing the process we're about ready to do. We're going to use our intuition. In the future, we will use algebra. So, let's think about what f is doing to our input. So, f of x equals 7x minus 3. If you had an input, then what would you do first to it? First, f says to multiply by 7. Then step 2, we would then subtract 3. To find an inverse then, we would have to undo what f did. So we are going to take this route. So f inverse would take our input and we would have to undo the subtraction of 3. So let's add 3 to our input. And then after we add 3, we have to undo the multiplication of 7 by dividing by 7. So notice we get f inverse of x equals x plus 3 all over 7. Now, let's check our answer. So we had f inverse of x equals x plus 3 all over 7. To check our answer, we must first find f of f inverse of x. So this means that we're going to put into f inverse. So x plus 3 all over 7. Now what does f say to do to that? F says I'm going to multiply the input by 7 and then subtract 3. So we'll multiply the input by 7 and then subtract 3. But the input is x plus 3 over 7. So we can cancel the 7's. And we have x plus 3 minus 3, which yields for us x. So notice f inverse acts, and then f, and f takes us back to what f inverse acted on. Now that's not enough. We have to show also that f inverse of f of x equals x. So f inverse of x will be f inverse of, now what does f say to do to x? It says multiply by 7 and subtract 3. So f inverse will be taking that input and adding 3 to it and then dividing by 7. So what are we going to put in for x? Our input is 7x minus 3. 7x minus 3 plus 3 is just 7x. Cancel the 7's, we get x. Now, since both of these return x, we are correct. So here we have two functions, and we want to verify that they are inverses of one another. So, in other words, what we have to do is we have to take f of g of x and show that equals x, and then we'll have to show g of f of x is x. So f applied to g of x will be f applied to 7x plus 8 over 3 minus x. So this means f is going to get applied to that input. So f says take 3 times the input, subtract 8, and then take the input and add 7. Where am I getting this from? 3 times the input minus 8, input plus 7. But now my input is this fraction. So 7x plus 8 over 3 minus x. And then likewise in the denominator, 7x plus 8 over 3 minus x. So here in the numerator, I can take the 3 times, this is like 3 over 1, distribute that throughout the numerator, and we would get 21x plus 24 all over 3 minus x. That's going to then subtract 8, and that is equal to, then that is all over 7x plus 8 over 3 minus x plus 7. So now, the best thing to do is think about this as 8 over 1 and 7 over 1. And then we're going to look at those four denominators. 3 minus x, 1, 3 minus x, and 1. We're going to multiply everything by the LCD of those four denominators, which is just 3 minus x. Now what that does is it's going to cancel for us so that we only have a single fraction instead of several fractions. So what do I mean? I'm going to take this fraction, multiply by 3 minus x. So we have 21x plus 24, and that is over 3 minus x. We're going to multiply by 3 minus x. Minus 8 over 1 times 3 minus x. Now we'll do the same thing in the denominator. 7x plus 8 over 3 minus x times 3 minus x plus 7 over 1 times 3 minus x. Now this is equal to, some things cancel, right? We have 3 minus x and 3 minus x cancel. That will leave us 21x x plus 24. And then we have 8 over 1 times 3 minus x, but that's actually negative 8 times the 3 minus x. So we're going to distribute the negative 8 throughout. And so we obtain negative 24 plus 8x. Now let's look at the denominator. 3 minus x and 3 minus x likewise cancel, and we get 7x plus 8. And then we can distribute the 7 throughout the 3 minus x, and we obtain 21 minus 7x. Now what are we left with in the numerator? 21x plus 8x is 29x. And then 24 minus 24 goes away. And then in the denominator we have just 29, and so this yields x. So now we have to find g of f of x. So g of f of x will equal g of what's f of x? F of x is 3x minus 8 over x plus 7. So now what does g say to do to that? G says we take 7 times that input, add 8, and then 3 minus that. So we have 3x minus 8, x plus 7, 3x minus 8, x plus 7. So we can distribute that 7 throughout the numerator. So 7 times 3x minus 8, because this is like 7 over 1. So we have 21x minus 56 over x plus 7, add 8. Then the denominator is 3 minus 3x minus 8 over x plus 7. Now to simplify this, because we see a fraction within a fraction, we can multiply by the denominator x plus 7 over x plus 7. Now what that's doing is going to cancel this fraction. It's going to cancel the denominator from this fraction, and then cancel the denominator from this fraction. But we have to distribute this to both of these two terms, and this to these two terms. So we'll take the x plus 7, and we'll multiply times that, and then we will multiply times the 8. And so what we obtain is 21x minus 56, because the x plus 7's cancel, and then we multiply by the 8, so we get plus 8x plus 56. Now in the denominator we do likewise, so we take the x plus 7 times the 3, and we get 3x plus 21 minus, now we're going to distribute the x plus 7 times this fraction, but that means the x plus 7s are going to cancel, and so we have minus the quantity 3x minus 8. And so we obtain 21x plus 8x will be 29x minus 56 plus 56, those go away. And in the denominator, we have 3x plus 21 minus 3x plus 8. And so we get 29x over 29, which is just x. Now because f of g of x is x and g of f of x is x, we can finally say that f and g are inverses. So here we have two functions, and the goal is to determine if they are inverses. That's the first goal at least. So f of g of x equals f of the square root of x plus 1. But now what does the function f say to do to that input? Well, f says that I take the input and I square it and then subtract 1. So we'll take the input of the square root of x plus 1, we will square it, and then we will subtract 1. And this yields for us x plus 1 minus 1, which is x. Now, that looks good. Let's try g of f of x. So g of f of x is g applied to x squared minus 1. So, what's g say to do? It says to take the input, add 1, and then take the square root. So there's our input. Let's add 1 and take the square root. So we have the square root of x squared. Now before you say that that is x, it's actually the absolute value of x. In case you don't believe me, let's look at the square root of x squared if x equals -5. We would have the square root of -5 quantity squared, which is the square root of 25, which is 5. So if we put in -5 into the square root of x squared, we get out +5. We're getting the absolute value of our input. So the square root of x squared is the absolute value of the input x. So notice the absolute value of x is not necessarily x. So therefore, f and g are not inverses. Now, is there any way, in the second part of the question, if they are not inverses, can we exclude any values of x from their domain in order to make them inverses? To do this, let's look at their graphs. So, we have the graph of f, which is a parabola, shifted down 1 unit. And then we have x squared minus, the square root of x plus 1 is going to be our square root function. So now, if we take a look at f, we have this full parabola, and g, we have it reflected about the line y equals x, but that is actually not the whole parabola reflected. It is just a portion of it. It's this portion of f reflected. So what we can do is we can erase part of f. If we erase part of f and we focus only on what I've highlighted here, then f and g would be inverses. So let f of x equal x squared minus 1 when x is bigger than or equal to 0. Then they will be inverses. Then f and g will be inverses. Now, you can tell that from up here, if x is bigger than or equal to 0, as it's an input for f, then the square root of x squared will equal the absolute value of x, but x isn't negative, so therefore the absolute value of a number that's not negative is itself. So how do we find an inverse of a function algebraically? Well, we start by replacing f of x with y. We switch x and y and solve for the new y, and then our new y is actually f inverse of x. So here we have a function. It's 1 to 1, so what we're going to do is find its inverse algebraically. So we start off by replacing f of x with y, and now we're going to switch x and y. So we have x equals 8y over 2y minus 1. Now let's multiply both sides by that denominator to clear the fractions. So 2y minus 1, I'm going to multiply both sides of our equation by that. So x is going to get multiplied by 2y minus 1, and then 8y over 2y minus 1 will get multiplied by 2y minus 1. On the left, we'll distribute, and we get 2xy minus x, and on the right, the 2y minus 1's cancel. Now, we're solving for y, so we need to get y on one side. So let's subtract 2xy from both sides. So we get negative x equals 8y minus 2xy. Now we have two terms on the right that have y. Let's factor out the y. Now, we can undo the multiplication that we see by dividing by 8 minus 2x on both sides. So we have negative x over 8 minus 2x equals y. Therefore, f inverse of x equals negative x over 8 minus 2x. So let's look at this function f. So we have f of x equals x cubed plus 2. So that is, let's graph it first, the cubic function shifted up 2 units. Now let's find the inverse. This is y equals x cubed plus 2. We're going to switch x and y. And this gives us x equals y cubed plus 2. We're solving for y, so we'll subtract 2 from both sides. Now we'll take the cube root of both sides. So y equals the cube root of x minus 2. So f inverse is the cube root of x minus 2, which we know the graph of that is the cube root function shifted to the right 2 units. Now what you notice here is that there is a relationship between f and f inverse. And their graphs, I should say. What is the relationship? Well, let's think about switching x and y. if we switch x and y, when is that not going to matter? It's not going to matter when x equals y. So let's graph the line x equals y, or y equals x. And what you notice is there is a connection to these two graphs by letting y equals x be the mirror about which we can do a reflection. So if we reflect f about this line, we get f inverse. So the graph of f inverse is the graph of f reflected about the line y equals x. So if we look at this example, here's f. We want to graph f inverse. Well, let's draw the line y equals x. And we can think through the points. Whenever we find f inverse, we are switching x and y. So -3 will stay. 0, -2, let's switch x and y, will become -2, 0. 3, 1 will become 1, 3. And the point 4, 5 will become the point 5, 4. And now we can connect those points. You'll notice that whenever we cross the line y equals x, we intersect the graph of f. So the red graph is f inverse.